So I just have a few short anecdotes about important things that Bob Von Driel has done for me and for my students. I started doing high resolution, more or less high resolution X-ray scattering as a postdoc, but at the time I was only interested in one Bragg peak. We were looking at rare gas films absorbed onto graphite. And it was not until fullerenes came along in the 1990s that I started actually paying attention to the relative intensities of more than one Bragg peak to try to determine where the atoms were. And fullerenes were a perfect laboratory for learning this because the first one we looked at was face-centered cubic with a fairly obvious structure, although we were surprised by some things that showed up there. And as we kept making more and more, oh, and the other great thing about fullerenes is that the samples are simple enough that physicists can make them. And so we went our way through making them and discovering properties. We got to this one, which is, this is rock salt at high temperature, but then something bad happens to the diffraction pattern when you cool it down. Just let this cool down slowly to room temperature, and you get a diffraction pattern like this. And so we were trying to figure out what this was. By the way, I'll mention that Gabor Aslani here is the fellow who invented charge flipping. But we were trying to index this, and I don't think that the challenges come from, or part of the challenges in complicated powder diffraction don't come from really big samples like proteins or the McGovernite that we just heard about. I think that, or at least the vein that I seem to keep mining, is what's the crummiest data that you can resolve a structure from? And this was a good example of it. You wouldn't trust any indexing of this, and you especially wouldn't trust any indexing of it, since it always gave, it seemed to give orthorhombic space groups, structures, lattices, with a 9.1 angstrom d-spacing. Fullerenes are 10 angstroms in diameter, and every other fullerene that we had ever seen, the smallest lattice parameter, the smallest was governed by the interfullerene. How could you have an interfullerene distance of 9 angstroms? And the answer is that they're bonded together into chains. And so you have this sort of pearl necklace. You can't isolate these because it requires, well, it's held together, it's kind of templated by the alkali ions that are in here. But in order to model this, I had to learn much more diffraction than I had, and I had to learn a tool that was that was essentially new to me, which is this thing called GSAS. And I really approached this with trepidation, and finally screwed up the courage to ask this god of crystallography if he would deign to help me figure out how to do this. As I said, I was not used to more than one Bragg peak, and figuring out, how are you going to deal the space group symmetry and the fractional occupancy of the sites together. Bob was so generous with helping me figure out how to do this, and in a way that was very educational. He'd say, well, try this, and I would, and then I could come back and say, well, yeah, but, and he really was extremely helpful. We've had other people talking about rigid bodies in GSAS-I, the PC version, and what a nightmare it was. Abandon all hope, ye who enter here, summarizes, except this is the only way to do it. Bob had developed these tools in a way that one could eventually figure out how to use. Great thing about speaking relatively late in a program is other people have already said the things that you were going to say. So if you didn't believe a structure derived from that previous diffraction pattern, Ashvia showed you what she did to actually figure out these structures. And it is correct. These diffraction patterns run from sort of close to the, well, 28 degrees in this previous one. This would be a 2 theta, oh yeah. This would be a 2 theta of 28 degrees in this pattern. Come on. That is to say halfway across the pattern out to about 90 degrees. So you don't see a lot of resolution in that sample. We certainly had better samples when we did this to get all of that diffraction data and make sense of figuring out the weights and so on. Well, this isn't a seminar, so I'm going to skip that. And I'm going to tell you, whoops, stop showing a punchline. I will get there. Okay, good. So another problem. With high resolution diffraction, often you learn more about your sample than you wanted to. And a conspicuous occurrence with that is anisotropic strain broadening. The peaks aren't all the same width. And there were some attempts to look at that in various ways. So the name of Dave Cox appears in this is GSAS documentation, both in the profile correction for the axial divergence and in the use of a pseudo-white line shape. And I guess this is a good time to finish the punchline. Dave Cox sends his regards and is very happily moved with Martine. Many of you know the two of them into a continuing care retirement community on Long Island, and that's not a fake picture. They really do look that good, that happy, and it's wonderful to see them. This is some publicity that was published in a concert program recently that we attended. Anyway, so I had this idea about anisotropic strain broadening, tried to implement it into, well, I wanted to try to implement it into something, and the only code that I could get my hands on, because this was still at an experimental stage, was ProfPV, which was the Brookhaven adapted, directly or through several stages from Rietveld code by Brian Tobey, among others. And so as I was writing this talk, I was starting thinking, gosh, ProfPV, what actually is the history of that program, that Rietveld program? And so, you type in ProfPV onto Google will show you anything. And to narrow it down, I put in Cox as the person that I thought would be. So this is the only thing. No, how did I do that? This is the only thing that Google would show me when you type ProfPV. And technically it's right. I mean, see, here's ProFPV, and here's somebody named Cox who put it together. So just like the Greater Seattle Aquarium Society.
I stole that. Originally.
This is an unexpected hit. Okay. So we actually implemented that. I implemented that in ProfPV, but not to try to do the crystallography. That was just a Labai fit. Bob came on board and coded the model into GSAS, and I could only find images of the. I certainly don't have this data sitting around anymore. But if you look at it is absolutely critical to include anisotropic strain broadening in this particular nasty material in order to get a crystallographic fit that anybody could plausibly accept. I've got one little anecdote without a slide that I want to tell about Bob. When he called me up and said, I've got this idea for proteins, and everybody else laughs at me. And I said, I had to be in line. Sure, come on ahead and try it. I owe you. And a remarkable thing, nobody else has mentioned this. When he came and was running his experiments, grinding up protein powders and so on at NSLS, I don't think he once looked at his email. I don't think he once answered a telephone message. He just worked. He was working on the science continuously. And that's really an impressive model, I think, for his level of interest. All right, well, I'm just going to flip ahead. Oh, I see what I keep doing. That responds faster than that. Anyway, I
don't know what you wanted to do there, but.
I know, I just want to show that I don't want to do that. Thank you. With Brian Toby, I just want to mention the improvements to GSAS, or the improvements that are embodied in GSAS-II. Here's some recent work that we've done, starting with an image like this. These are interesting materials that are good for separating ethane from ethylene, which is a pretty important industrial process that I'm working with in a collaboration that I'm not going to bother to tell you all about. But the tools of GSAS-II in running beamline 17BM at the advanced photon source to go from a data set like this to an image like this, which tells you what's going on. What's going on is pretty straightforward. Here, it's one phase and then it's another phase. But then to get refinable powder diffraction data from a 30-second exposure here and be able to turn it into a molecule that nobody would have ever believed would exist in this material is just a remarkable contribution. So thank you for all of these things. I think it's very well said that people for generations will be thanking Bob Condreel for his contributions to all of our work. So thank you, Bob. And I would also like to say thank you very much to Brian and Jim for organizing this and giving us all a chance to get together. It's such a pleasure to see you all.
By the way, Bob, just want to warn you that we will have question and answers, but you get to give all the answers. I mean, this is all your collaborative work, so you should be able to answer it all, right?